Alright, so let's talk about RAID in server systems. Now, you're probably familiar with at least some of the different RAID levels because they do exist in desktop systems, but in the server system they really shine. Let's review some of the different RAID levels and talk about how they can be used or leveraged in a server system. Now remember that RAID stands for Redundant Array of Independent Disks. It originally stood for Redundant Array of Inexpensive Disks, and the idea was to take several small hard drives and combine them into a larger hard drive. This allowed users to have larger file systems without spending as much money on the drives themselves. Even in today's world, it's less expensive to buy 500 gig or 1 terabyte SSDs as it is to buy an 8 terabyte SSD as far as the cost per gigabyte is concerned. With that in mind, the first RAID level, so to speak, was JBOD, or just a bunch of disks. Essentially, you could get a collection of disks that would be presented to the operating system as a single disk, and as one disk was filled up, it would simply begin writing data to the next disk in the array, and so on and so forth. There wasn't any performance increase in this particular level of RAID, nor any redundancy. The advantage was if a single drive failed, you only lost the data on that drive, and you could, theoretically, use all of the space on all of those drives as though it were a single drive. In order to improve the performance, we came up with RAID level 0, which essentially striped the data across multiple disks. So rather than waiting until a disk was full to start writing to the next one, we would divide up a file and write equal parts of that file to all of the disks in the array. This essentially multiplies the performance, the read-write performance of that array by the number of drives. So if we have a single drive that works at 100 megabytes per second, a 2-drive RAID 0 array would essentially double that to 200 megabytes per second. The space is similarly multiplied. A 1 terabyte drive alone put into a RAID array of two 1 terabyte drives would give us 2 terabytes worth of space. RAID 0 gives us the maximum amount of performance and storage space of any of the RAID levels. However, it has a significant downside. If any one of the drives fail in that RAID array, all of the data is lost. And as those arrays get larger and larger, or the number of disks in that array gets larger and larger, the likelihood of a disk failure increases significantly. So while you get great performance and storage space, the data is at severe risk of being lost. In order to combat that, they came up with the next RAID level, which is RAID level 1. RAID level 1 is specifically interested in making sure that data is redundant and not lost. As such, RAID level 1, or mirroring, mirrors all of the data bit for bit between two hard drives. In terms of performance, this doesn't really improve the write performance of a particular operation because the data still needs to be written to both disks. However, read performance can be improved depending on the RAID controller since there are two disks to read a file from. If it can get half the data from one disk and half the data from another disk, it can dramatically improve the read performance even if the write performance is not improved. But the significant benefit of RAID 1 is that if a drive fails, we haven't lost any data. There's an exact copy of that data readily available on another drive. Storage space, however, suffers a bit because we essentially have to pay for twice as much storage as we actually end up getting. If we have two 1 terabyte hard drives in RAID 1, we only have 1 terabyte of usable space because there's a perfect mirror on that other 1 terabyte drive. In an attempt to get the best of both worlds, RAID 10 combines the striping of RAID 0 and the mirroring of RAID 1. You'll need a minimum of 4 disks, but essentially what RAID 10 will do is stripe between mirrored pairs of drives. The striping will essentially multiply the performance of both read and write operations, and the mirroring prevents a single drive failure from destroying the RAID array. In an array of 4 disks, you can essentially lose up to 2 drives before you begin to lose data. However, if the 2 drives that fail are in the same mirrored pair, then you will lose all of the data in the array. Similarly, if you have a RAID 10 array of 8 drives, you could lose up to 4 theoretically, but if just 2 in the same mirrored pair fail, you'll lose that mirrored pair, that will break the stripe of data, and you'll lose all of the data in the set. So while there's better potential, lower risk of a drive failure causing data loss, because you have at least half of your disks that could fail, if the wrong disks fail, you can only truly survive one failure in a RAID 10 array. Similar to RAID 10, in order to promote performance while still maintaining redundancy, RAIDs 5 and 6 introduced a different method rather than a one-to-one mirror. RAID 5 uses what's called distributed parity. As each file is written to the drives, it's broken up into a series of pieces. Each of those pieces is then run through an algorithm that calculates a small amount of parity data which is stored on the last drive. So for example, if I have 3 drives in RAID 5, the data that I'm writing is split up into 2 pieces, and then there is a third piece that is a mathematically calculated value that can be used to recover data that's lost. Think of a simple math equation such as 3 plus 5 equals 8. If I put 3 on a drive, 5 on a drive, and 8 on a drive, and I lose any one of those drives, I can figure out which number is missing. For example, if the parity drive, the drive that has the 8 on it, disappears, I know that the data that's supposed to be there is the 3 plus 5. Similarly, if my drive that's holding the 5 on it disappears, I can recover that simply by subtracting 3 from 8 and coming up with 5. Now, of course, the RAID 5 and RAID 6 parity is significantly more complicated than that, but you can see how a mathematical operation could combine any number of individual values, come up with an answer that can be used to reverse and recover whatever data was lost. RAID 5 essentially protects all of the data from a single drive failure. However, if 2 drives fail, just like in RAID 0, all of that data is gone. The advantage of RAID 5 is a significantly larger amount of storage space depending on how many disks you use. No matter how large your RAID 5 array is, you always lose only 1 disk's worth of space. So if I have 3 hard drives, 3 1 terabyte hard drives in RAID 5, I'll end up with 2 terabytes of usable space because that third drive will be used for parity storage. Similarly, if I have 8 1 terabyte hard drives in RAID 5, I get 7 terabytes of usable space and still only 1 terabyte is used for that parity storage. The performance, therefore, is significantly improved because I can read and write to multiple drives. However, RAID 5 requires a parity calculation, and in the desktop world, that calculation is typically done on the CPU, making RAID 5 significantly slower because every read-write operation takes time on the CPU to calculate the parity value before it can be written to the drive. In the server world, RAID 5 has better performance because the RAID calculations are actually done on the RAID controller itself, and they don't involve the CPU at all. This dramatically improves the performance of RAID 5, but there's still an overhead involved in calculating that parity bit. Now, RAID 5 is rarely used in the server world because if a drive fails, realize that you have to rebuild that array by sticking in a new drive and having the RAID card recover the data that's supposed to be on that drive. The likelihood of another drive failing in a RAID 5 array during that recovery is very high. As such, RAID 5 is not particularly popular in the server world. Instead, RAID 6, which is an improvement on RAID 5 that essentially protects the entire array from 2 drive failures, is much preferred. The downside is that you're going to lose 2 drives worth of parity space rather than just 1 drive's worth of parity space. Again, RAID 6 parity calculations are going to be done on the RAID card, and as such, introduce some latency into a RAID 6 read and write. So while you may get significantly more performance than RAID 10, and you still have at least 2 drives that you can survive failing, the performance may not be any better or worse than a RAID 10 array. Consider the following examples. Let's assume that all of the drives that we're going to use are 1 terabyte drives capable of 100 megabytes per second of read and write. I'm using nice round numbers in order to make the math a little bit more logical here. But you can actually calculate the real values and real performance of RAID arrays based on the performance of any drive that you choose. Let's look at 8-disk RAID arrays using these various different levels. Starting with RAID 0, we have the best performance and the most capacity. Those 8 drives will give us 8 terabytes of storage space at a whopping 800 megabytes per second of both read and write. However, remember, if any disk in that 8-drive array fails, all of the data is lost. Now, technically, RAID 1 can't actually operate on a 8-drive array. It's typically just mirroring between 2 drives. But let's assume that it's somehow a combination of RAID 1 and JBOD. So essentially a bunch of mirrored pairs that as one fills up, it just writes to the next one and the next one. In that case, our 8 drives would give us 4 terabytes of usable space, a 100 megabyte per second write, but a 200 megabyte per second potential read, because we've got 2 locations to read that data from. Because the drives are organized in mirrored pairs, we could lose up to 4 drives without losing any of the data. However, if a mirrored pair fails, meaning 2 drives fail, we could technically lose all of the data. So we can survive between 1 and 4 drive failures depending on which drives fail. Next, let's consider RAID 10. RAID 10 is going to improve on our RAID 1 JBOD weird array by giving us striping between those mirrored pairs. We're still going to only have 4 terabytes of usable space, but we've improved our performance up to an 800 megabyte per second read, if we can read from all of the drives in the array simultaneously, and a 400 megabyte per second write, a significant improvement over our single drive. We can also survive between 1 and 4 drive failures, depending on which drives fail. Now let's consider RAID 5. 8 1 terabyte drives in RAID 5 would give us 7 terabytes of usable storage, almost as much storage as our RAID 0 gives us. It would also give us roughly 700 megabytes per second read and write, minus whatever overhead is used in the parity calculation. With a good RAID card that has onboard cache memory and a powerful CPU built into that RAID card, that overhead might be negligible and we might actually see the full performance of that. However, in a desktop world where the CPU is doing the calculations, we may actually see less performance in that RAID 5 drive than a single drive. RAID 5 will also guarantee that no matter which one of the drives fails, we will still have all of our data. However, it will only allow for 1 drive failure. RAID 6 will give us 6 terabytes of usable space, which is more than RAID 10, will guarantee that 2 drives can be survived from failing, and will get a decent 600 megabytes of read and write, minus whatever latency the parity calculation incurs. Again, on a good RAID card, that latency should not be significant, and we'll actually see that full 600 megabytes of read-write. Realize that this would essentially give us the capacity and performance of a 6 terabyte solid-state drive. 8 1 terabyte hard drives could be had for less than $400. However, a 6 terabyte SSD, if it existed, would be close to $700 today. As I've mentioned a couple of times, the performance of RAID arrays is significantly dependent on the actual RAID controller. In the desktop world, RAID controllers are typically built into the CPU or the south bridge, and they usually use CPU and system memory resources in order to perform their tasks. In the server world, we want to stay away from CPU-dependent hardware as much as possible. And as such, we have RAID cards, PCI Express cards that connect to SATA or SAS drives and provide RAID functionality. These RAID cards have built into them their own CPU RAID controllers and a large amount of cache. In the olden days, 256 or 512 megabytes could be found on a RAID controller. Today, you can find 2, 4, or even 8 gigabytes of DDR memory built into that RAID controller card in order to accelerate read-writes from drives. In practice, this might make an array of hard drives, no matter what their performance, appear to be high-end SSDs because of the caching that's done in that memory. But realize those high-end RAID controller cards can cost a premium, over $1,000 per card, which in a server may actually be a very worthwhile investment to get significantly higher performance out of your drives. Less expensive RAID controller cards in the $300 range will have less memory or a lower performance CPU built into that RAID card, will still offer a lot of performance per dollar, but may not have all of the features of a high-end RAID card. Cheap RAID cards, which are less than $100, will oftentimes still offload their RAID tasks to the CPU and system memory, which essentially negates the benefit of having that RAID controller card. Now, you may have picked up on the fact that if DDR memory is being used on the RAID controller in order to cache reads and writes, that DDR memory is volatile, and if power is lost during a write operation, in other words, the operating system has tried to write something to a hard drive, the RAID card has cached it to improve responsiveness, but hasn't actually written it out to persistent storage yet, there's a potential for data loss. And as a result of that, manufacturers include what is called a backup battery unit. That battery backup unit has enough energy to essentially power the DDR memory module in case of a power failure to keep the data in that memory module so that when power is restored, it can write it out to persistent storage. Without that battery backup module, using cache or using that DDR memory on a RAID controller is very risky, and there's a very high likelihood of losing the data on that drive. Those battery backup units add cost, but again, the performance and stability of the server are at stake. Now, apart from the standard RAID levels 0, 1, 10, 5, and 6, there are other RAID levels that exist that are combinations thereof, such as RAID 50 and RAID 60. Which is essentially a stripe of RAID 5 arrays or a stripe of RAID 6 arrays. These can be used to increase performance, especially in significantly larger drives, but oftentimes require more expensive RAID controllers in order to create that level of RAID array. Consider as an exercise the RAID level that would be required in order to guarantee that the RAID array could survive 4 drive failures. Realize that our standard RAID arrays can't do this. RAID 10 can only really guarantee 1 drive failure. While it's possible that it could survive up to 4 in an 8-disk array, it can only guarantee 1. Similarly, RAID 6 can guarantee 2 drive failures, but it can't guarantee survivability of failures more than that. So try and come up with a RAID level that would be a combination of these different levels that would be able to survive and guarantee survivability of a 4-disk failure. Now that I've got you all excited about RAID, I have to break some bad news to you. While RAID is a really cool technology and it exists in a lot of servers today, RAID is going away. The layers of abstraction that have been introduced with virtual machines and software-defined RAID have actually exceeded what the hardware RAID can do. And there are systems out there that can provide better performance and actual better data integrity than our hardware RAID systems can. I'd encourage you to look into alternatives to RAID from a software standpoint, see what you can find. But it's outside the scope of this class and this video for me to go into those in more detail. So you'll need to know the details of RAID for this class, but in the real world, you'll need to move beyond RAID.